Can something as ordinary as a bouncing oil droplet behave like a quantum particle? Surprisingly, yes, and this brings us to a fascinating idea: non-locality in classical systems. In certain experimental setups, tiny oil droplets placed on a vibrating fluid surface start bouncing and walking across the surface, guided by the waves they themselves generate. This feedback loop between droplet and wave is strikingly similar to the pilot wave theory, an early interpretation of quantum mechanics proposed by Louis de Broglie, where particles are guided by an invisible wave field. But how is this quantum-like behavior possible in a classical setup? The answer lies in the memory of the system. Each droplet interacts not only with the wave under it, but also with the cumulative pattern of waves left behind from previous bounces. This history-dependent behavior introduces a form of effective non-locality. The droplet's path is influenced by its past, and the entire wave field carries information about where the droplet has been. So, what does this mean for our understanding of quantum physics? These pilot wave analogs have been shown to mimic several hallmark quantum effects, such as tunneling, interference, quantized orbits, and even analogs of the double-slit experiment. But are they truly quantum? No, these are still classical systems driven by deterministic rules. However, they raise deep questions. Could quantum behavior arise from deeper classical processes we have yet to discover, or are these analogies just clever illusions? While most physicists agree that these systems cannot fully reproduce the randomness and entanglement of true quantum mechanics, they do challenge the idea that quantum phenomena are forever beyond classical intuition. They offer a rare bridge, a way to see quantum-like behaviors in the lab using everyday materials. And that is what makes them so intriguing. In the dance of droplets and waves, we glimpse echoes of a quantum world through a classical lens.
Quantum physics is famous for being strange, particles behaving like waves, teleporting properties across space, existing in two places at once. One of the most puzzling features of the quantum world is non-locality. The idea that a particle here can instantly affect a particle there, no matter how far apart they are. Einstein called this spooky action at a distance. It sounds so bizarre that we usually think it belongs entirely to the microscopic realm of electrons and photons. But what if something similar could be seen in a puddle of oil? In recent years, physicists have discovered a remarkable system that seems to echo some of quantum mechanics' weirdest behaviors, but in a purely classical, visible, and touchable setting. It all started with bouncing oil droplets. Yes, really. Here's what happens. Take a vibrating oil bath and place a tiny droplet of oil on its surface. Instead of sinking or floating, under the right conditions, the droplet starts bouncing rhythmically. As it bounces, it creates ripples in the oil surface. Those ripples bounce back, influencing the droplet's next movement. And this feedback loop turns the droplet into something more than a simple particle. It becomes a walker, a droplet guided by the waves it itself produces. But here's where it gets weird. These bouncing droplets can begin to mimic behaviors that until now were thought to be exclusive to the quantum world. For example, in one version of the experiment, the droplet is placed in a confined area like a corral made of walls. When this happens, the droplet starts to follow specific orbits, creating patterns that look eerily like quantized energy levels in atoms. Or send the droplet through a pair of slits, and its accumulated behavior, recorded over time, starts to resemble the interference patterns seen in the famous double-slit experiment with electrons. That's the one where a single electron seems to interfere with itself as if it's going through both slits at once. The oil droplet isn't literally splitting in two, of course, but the waves it rides on can interfere, steering the droplet in complex, wave-like ways. So, what does this mean? Some researchers see these experiments as analogs, ways to model aspects of quantum behavior using classical systems. They're not saying the oil droplet is a quantum particle, but the pilot wave theory, once proposed as an alternative to the mainstream interpretation of quantum mechanics, gets a boost from this. According to that theory, particles are always guided by a hidden wave. In standard quantum mechanics, this wave exists in an abstract mathematical space. But with the oil droplet, the guiding wave is literally on the surface. You might ask, is this just a coincidence? Could these droplets actually help us understand quantum physics better? That's a hot debate. Critics point out that the analogy only goes so far. Quantum particles can be entangled, exhibit superposition, and collapse wave functions, behaviors that oil droplets simply don't replicate. But supporters argue that even partial analogs can offer fresh intuition. After all, if we can recreate quantum-like phenomena with ripples in oil, maybe we've been thinking too abstractly about what quantum mechanics really describes. And there's a deeper question here. Is quantum behavior truly fundamental? Or could it emerge from some deeper, deterministic, and perhaps even classical process? The oil droplet experiments don't answer that, but they nudge the door open to new ways of thinking. Could the universe itself be a vast ocean of waves and walkers, with particles tracing out paths influenced by invisible fields? For now, the bouncing droplet remains a fascinating metaphor, a laboratory trick that seems to whisper secrets of a much deeper theory. Whether it's an insightful analog or just a beautiful coincidence, it reminds us that sometimes the universe's strangest behaviors might have more in common with dancing oil than we ever imagined. The non-locality paradox in classical systems emerges from surprising experimental results where macroscopic oil droplets bouncing on a vibrating fluid surface appear to mimic behaviors typically associated with quantum mechanics, such as interference, tunneling, quantized orbits, and apparent non-local correlation. This challenges the conventional assumption that quantum weirdness arises solely from the microscopic world, suggesting that non-local-like phenomena may emerge in classical deterministic systems under the right conditions. In the experiments of Yves Couder and Emmanuel Fort, oil droplets on a vibrating bath began to exhibit behavior that resembled the quantization of angular momentum and interference patterns, hallmarks of quantum particles. It's like seeing marbles on a trampoline recreate the famous double-slit experiment, leaving you to wonder whether marbles too have a quantum mind. Non-locality in quantum mechanics refers to the apparent connection between distant particles, where the measurement of one particle seems to instantaneously influence the other, defying classical notions of locality and causality. In the classical droplet system, the non-locality behavior arises not from actual quantum entanglement, but from the interaction of the droplet with its own wave field, which spans a larger region of the fluid bath. This wave-mediated memory stores information about past trajectories, influencing future paths in a way that mimics non-local dependence. A droplet moving across the bath generates a wave, and this wave in turn guides the droplet, causing it to avoid or favor certain paths depending on previous interactions. Similar to how quantum particles are influenced by the entire experimental setup. It's like walking across a flexible floor that remembers your footsteps. Your future steps are redirected based on the echoes of where you have been. The core mechanism enabling this paradox is the pilot wave dynamics. The oil droplet continuously generates ripples on the vibrating fluid surface, and these ripples reflect off barriers and interfere with themselves. The droplet then interacts with this self-generated wave field, which contains history-dependent information about its past behavior and environmental boundaries. This feedback loop produces behaviors that look like probabilistic outcomes, even though the underlying dynamics are completely deterministic. In a circular corral, the droplet eventually settles into specific orbits, resembling the quantized energy levels of an electron in an atom, despite no quantum effects being present. It's like a person walking through fog that thickens where they just walked, forcing them into specific paths over time, even if they never consciously choose them. These experiments show that emergent complexity can produce behavior that mimics quantum phenomena without invoking quantum mechanics itself. They offer a macroscopic platform for studying quantum-like dynamics in real time, shedding light on how memory, feedback, and field mediation may play roles in systems traditionally seen as random or non-intuitive. The trajectories of the bouncing droplets in a two-slit setup form interference like fringes on the detection screen. Even though each droplet follows a definite path, it's like tossing pebbles through two holes in a wall, but they somehow land in a pattern that only a wave could create. The vibrating bat supplies continuous energy that sustains the droplet's motion and the pilot wave field. This energy flow allows the system to behave as a non-equilibrium oscillator, where the interaction between droplet and field leads to the storage and propagation of information over time. Under certain conditions, a droplet exhibits tunneling-like behavior, passing through a barrier it would classically bounce off because the surrounding wave influences its approach long before contact. It's like driving toward a foggy wall that dissolves only if the echo of your horn matches a special pattern. Your pass signals help determine if you pass or not. From an information theoretic perspective, these bouncing droplet systems store path-dependent information in the fluid surface, allowing for non-markovian dynamics, where the future state depends not just on the present, but on the entire history. The Wavefield acts as a distributed memory, embedding information about the droplet's past and integrating it into its motion. The droplet avoids areas where its past waves have interfered destructively, exhibiting behavior that appears probabilistic but is actually guided by hidden variables in the fluid surface. It's like navigating a maze where the walls shift depending on your memories. The map isn't fixed but rewritten by your previous steps. These classical analogs to quantum systems may offer new pedagogical tools, model systems, and even technological insights into how wave-particle duality and non-locality might be engineered. Researchers are investigating whether fluid-based logic systems could mimic quantum decision trees using pilot wave dynamics, offering a new type of analog computing. It's like building a computer that thinks by throwing stones into ponds and reading the answers from the ripples that form patterns of logic. Despite their elegance, these droplet systems do not capture all aspects of quantum mechanics. There is no true superposition, entanglement, or wave function collapse. Additionally, while the droplet interference patterns resemble quantum results, they require external energy input and do not replicate the full probabilistic structure of quantum mechanics. It's like building a shadow puppet that dances like a human. It may mimic the moves, but it does not have the same internal structure or motivation. The study of droplet-based quantum analogs invites a re-examination of the boundaries between classical and quantum physics. Future investigations may foster new interdisciplinary models involving fluid dynamics, nonlinear systems, information theory, and even philosophy of science. Some theorists speculate that these results could support pilot wave interpretations of quantum mechanics, where particles are guided by real wave fields, an idea originally proposed by de Broglie and Bohm. It's like discovering that the ghosts in the machine might just be clever echoes in the gears, showing that mystery can emerge from the ordinary if tuned just right.